Hello, my name is Maxim and today I want to present you visual odometry, and it's a part of assignment number 2 for sensor fusion. And today we will discuss what is visual odometry, where is implemented, where is not possible or hard to implement, what is the differences between SLAM and visual odometry, how it works, feature detection, camera motion from the optical view, sorry. And first of all, what is visual odometry? Yeah, visual odometry, it's a process of incrementally estimating the pose of the vehicles by examining the changes that motion includes on the images of in-board cameras. And here you see our input, yeah, just from a camera, just because of it's a visual odometry, it's based on the cameras, and the results of that. Yeah, just we have some access right here. Yeah, just and we see how we're going, and right now we will have a turn. Yeah, just right here, and we see how it defines. Yeah, just and right here, and we see how it turns, and we see the results of the on the cameras. Okay, where is implemented? And why do we need visual geometry? Just because of we have GPS denied environment. For example, on the pictures you see Mars exploration rover mission. Yeah, just and it's their product. And we have underwater tunnels, parking, huge buildings, and so on. And we have a problem with GPS. And of course, in big cities with skyscrapers or just high buildings, we have a beam reflection, and that's why in some of the center of the cities we have a tolerance for detection. It's 10 meters. Visual geometry is not affected by wheel slip. You see these pictures almost from Mars. Yeah, just icy sneakers, but it's a joke. We have sand here, ice, probably in different environments, rain, and so on. And if we have low friction coefficient on a wheel, yeah, just we will have problem with wheel odometry. Visual odometry can be used as an addition to wheel odometry, GPS, EMU, laser odometry, and so on. We have classical pair of technology. It's GPS plus EMU. But if we have GPS denied environment, yeah, just and EMU accumulated errors, yeah, just without GPS, and wheel odometry is not working quite well with sand, ice, rain, and so on and so on. Yeah, just that's why visual odometry can be used as a great addition to this classical, yeah, just technologies. And it's more accurate trajectory estimates compared to, for example, wheel odometry, and we discussed it. And EMU, yeah, just because of EMU accumulated errors very fast. Yeah, just visual odometry not it's very low. And for example, visual odometry as well could be implemented not only two-dimensional estimation, yeah, just but three-dimensional. And as you see on the pictures below, yeah, it could be using, for example, for drones, yeah, just or for helicopters or for planes or for satellites and so on, where is not possible or hard to implement, sorry. We need sufficient illumination in the environment. If we have, if on the pictures in the up picture, if we have not enough light, yeah, just camera it not works quite bad. Yeah, just it's not work. Dominance of statistics seen over moving parts. Just imagine you stand in the grounds and some of goings, yeah, just to the left, to the right, something run, and so on, and you don't understand based only on pictures, picture by picture, yeah, just where is a static, where is not static, where is a moving, and so on. And it's a real mess right here, and we need more static scene than moving scene. And third one, enough texture to allow apparent motion to be extracted. As we can see at the below picture, for example, even for human eye, yeah, just it's not enough data, yeah, just to understand is a fast we're going fast or we're going slow and so on, just because of if we have some lumps, yeah, just right here, or we have some trees, yeah, just nearby roads, we understand how it moves, yeah, just and understand, okay, it's quite fast or not fast. But if you have nothing, yeah, just it's a quite challenging to detect. Sufficient scene overlap between frames. When you have really small frame, for example, yeah, just and you want to save on compilation, and it's not enough, yeah, just on the same on the two frames, yeah, just go one after another one to take the same features, yeah, just it could be a problem here. And heuristics, it's more okay, probably better to explain it on an example. You sit in a car and you look at the bus, for example, yeah, just huge huge yellow bus, and you relaxedly look at the bus, and this bus started off going, but you understand in the first second that you start off how to say, you start off moving, yeah, just because if you looked at the bus and thought, yeah, just it's a zero, it's a static element, and probably it's standard situation for drivers, or probably for me. Why do we need visual geometry if we have SLAM? Good question. Visual geometry aims to definition of the trajectory. SLAM aims to trajectory and the map. Yeah, just and visual geometry can be used as building blocks of the SLAM. Yeah, and in 95%, yeah, just all of the SLAM algorithms has visual geometry inside it. But why do we need SLAM? Yeah, just because of the output of SLAM is upper picture. Output of visual geometry is a below picture. The answer is application. If we have embedded system, yeah, just and we need only trajectory, probably we don't need to overload our system on the not needed data. Yeah, just because of the choose between visual odometry and visual SLAM depends on the trade-off between performance and performance and consistency and simplicity in implementation. For example, you goes from one city to another city for 10 hours, yeah, and you should, yeah, just somewhere keep all of the map, yeah, just in your history and so on and so on, and always, yeah, just compare your estimation with from previous frames and so on. And you see, it's a kind of not needed algorithms or space or additional load to the system in some cases. Yeah, just if you need real-time performance, yeah, just without the need to keep track of all of the previous history on the camera, probably visual odometry is the best case for you. How it works, yeah, just we will look at a little bit video. We have input, yeah, just it could be frames from single, stereo, or fisheye cameras, and for of course we need image correction or undistortion. And you see, for example, upper picture is colored, below picture is gray. It's gray colored. Feature detection and optical flow. We will discuss it in details on the next slide, but you should understand these green points, yeah, just machinery consider as vital, yeah, just and we will see the differences based on that green points. Fourth, check flow field vector for potential tracking errors and remove outlets, and estimation of the camera motion from the optical flow. And you see the pictures, low picture, and we have three objects right here. Yeah, just and we goes if we go to the left, yeah, just objects go to the right. If we goes to the right, pictures goes to the left. If we goes to the scene, yeah, just objects goes more bigger, yeah, just but we understand and the differences between bigger and initial, yeah, just this frame and next frame, yeah, just gives us understanding what is going on with our speed and with our estimation. And of course we need to do it periodically, yeah, just we always will be assess current frame with the previous one, and next frame with the current one, and the next one with the next one, and so on. About feature detection, of course it's a computer vision, yeah, just and it takes like a few lectures to understand in the feature detection, but I'll explain it a little bit first. Just because of digital image, it's a lot of pixels, yeah, just and pixels has their position in the digital image and their intensity, color intensity, from 0 to 2055. And you see on 100 different pictures, yeah, just of the same building, probably we will notice, yeah, just this good feature with window. Why? Just because of its changing, yeah, just in colors in a specific shape, yeah, just like a triangle right here. And it's easier for algorithms to recognize it, yeah, just on a different slides, yeah. And of course if we are in a city, yeah, just probably corners or lines, yeah, just better solution right here. But in a rural, yeah, just environment, probably we should go with bubbles, yeah, just because of, for example, in the forest, yeah, there's not enough corners probably. And you see with the different shapes, with the different colors and so on, it's like a separate lecture just for good feature detection. And the problem is understanding, yeah, just and defining the same good features from the same photo, yeah, just on all algorithms, and we should check it. Camera motion from the optical flow. I especially put Wikipedia definition of optical flow right here, but I'll explain it on my own words. You remember Star Trek? Star Trek, when they travel from galaxy to galaxy, yeah, just when the stars suddenly goes to you, yeah, just and put some lights after that, yeah, just, or for example when you go to, on a car, and this little snow, yeah, just goes directly to you, yeah, just and you think you are in a space shuttle, yeah, just and it's a optical flow effect, yeah, just in your real life. And why do we need this? Yeah, just first of all, calculate optical flow and translation values from each point on a pair of frames. So as we discussed, yeah, just in the previous slides, yeah, just we have two frames, yeah, and we go directly right here, and we see how pixels, yeah, just changing their places, yeah, just and the picture below, yeah, just you see these green lines, yeah, just and it's a initial place of the pixel, yeah, just and the last place of the pixel. But we need to cut off some of the values from both sides. And why do we need this? Just for example, we are talking about white BMW, yeah, just on a picture. For example, yeah, just we're pedestrian, and BMW has their own speed and probably more than us, and it not it not means, yeah, just that we significantly increase the speed, right? Just because of, yeah, you see, and that's why we need to cut off, yeah, just from the calculation some um, statistical artifacts, yeah, and you see these red lines, yeah, just in the end of the picture. It's just because of um, effect of when you look at the horizon, yeah, just object is not moving, yeah, just almost, yeah, just, and your speed probably, yeah, just not well defined, but you look at the ground, yeah, just at your feet when you're running, for example, yeah, just it should be a huge um, huge speed of changing frames, yeah, just like this one. And that's why we need cluster the rest of the values. Just look at the middle of the picture, yeah, just it's a not green lines, yeah, just it's a more like green points, yeah, just that's why based on this information, yeah, just how it changed the distance, yeah, just between previous frame and current frame, when we could understand the depth map, yeah, just that what is going on, yeah, just okay, it's a far object, yeah, just and it, or it's a close object, just because of close object, when you are close and you look from the different angles, yeah, just it's change position significantly, but if it's on the horizon, yeah, just not moving probably at all. And calculate the differences between the minimum and maximum cluster centers, yeah, just understand their uh, position changing, yeah, just on our frames, and understanding their depth, yeah, just how far from us it is. It allows us calculate our speed, yeah, just, and our trajectory. So for today it's all. Thank you for your attention, and bye bye.